So in this lesson, we are going to look at the types of intermolecular forces. Which we will abbreviate IMF for intermolecular forces. All right, now remember, an intermolecular force is the force of attraction between particles. Okay, this is different than intramolecular forces. Okay, so if we were to look, for example, at water, water has an attraction to water. We know water is polar, causing a partial positive end and a partial negative end. And so this partial positive end is attracted to the partial negative, and this partial positive is attracted to the partial negative of this oxygen. So this right here is the intermolecular force. The intramolecular force is that covalent bond holding the hydrogen and the oxygen together. And this is just a quick review from a previous unit that we did with that activity that we did where we determined what the difference between inter and intramolecular forces was. All right, so let's look at our intermolecular forces, and we are going to list these from strongest to weakest, but the only rule in chemistry is there are no rules. So I'm going to give you these rules, but the reality is certain things will go against these rules. And I see these types of questions on the AP exam quite often. We're going to give, or not we, the exam makers are going to give you something that goes against what the rules are, and your job is to figure out specifically why that's the thing. Okay, so we're going to give you these rules, but just keep in mind there are exceptions to these rules because the only rule in chemistry is there are no rules. So our first one is the network covalent solid. And a network covalent solid are things that involve silicone, diamonds, and quartz. These are examples of network covalent solids. Diamond and quartz are both made up of carbon, all right, and the arrangement of carbon is different, giving a diamond a different property than quartz. Whoops. We then have ionic and metallic bonds. Okay, so we have ionic and metallic bonds. Ionic being things that contain a metal, nonmetal, or a polyatomic ion. Metallic bonds being just a plain metal. Now remember, guys, polyatomic ions are ions that are covalently bound together. All right, so a review from a previous unit. All right, hydrogen bonds are next. So in in biology, you learn that hydrogen bonds are the strongest bonds, but in fact, that's really not quite the case. Hydrogen bonds are, in fact, not the strongest. Network covalent solids are the strongest. Hydrogen bonds involve hydrogen with nitrogen, hydrogen with oxygen, or hydrogen and fluorine. Now, this is an attraction between. All right, so let's look at an example, and we'll use water as our example. All right, again, here's water, and let me draw water a little bit better. Water does have, I didn't draw the lone pairs up at the top, but we know that water is a bent shape, and it does have lone pairs. We've learned how to draw those. All right, and we do know that the oxygen is more electronegative, so it is a partial negative, and the hydrogen is less electronegative, so it is a partial positive. So we can do the same thing on this second water molecule. And we have an attraction between the oxygen of one molecule and the hydrogen of another molecule. So that's this particular one. So the hydrogen bond is not but the bond holding the oxygen and the hydrogen together. It is an attraction between an oxygen from one molecule and a hydrogen from another molecule. That is a hydrogen bond. All right, so this is the hydrogen bond. So be careful because students tend to get this confused. They see this particular bond and they say, oh, hydrogen bond. That's not the case. Water has the ability to form a hydrogen bond with another molecule of water. All right, and the same thing with our HN and our HF. These are attractions between two molecules because intermolecular forces are a force of attraction between particles, not within. All right. We have dipole-dipole. Okay. And this is going to be any polar molecule. And we've already learned how to draw dipoles, all right, and learned that polar molecules do have dipoles, all right. So if we were to look at, let's say, hydrochloric acid, all right, chlorine is more electronegative than hydrogen. So chlorine is a partial negative charge. Hydrogen is a partial positive charge. And hydrochloric acid is a polar molecule. There is no central atom. It is asymmetrical, making it polar. All right, so we have an attraction between the partial negative of the chlorine in molecule 1 and the partial positive of the hydrogen in molecule 2. So this is the dipole-dipole attraction, again, between molecules. Finally, we have our London dispersion forces. Which we can abbreviate LDF. Now, these are the weakest of our forces. So I am going from strongest down to weakest. All right. All substances have London dispersion forces to some degree. This is important. All right. Nonpolar molecules have London dispersion forces. Okay, so if it is nonpolar, we're going to give it a London dispersion. Now, London dispersion forces usually increase as molar mass increases. And the key word here is usually because the only, again, rule in chemistry is there are no rules. All right, so why is this the case? Why does it usually increase? Because something with a higher molar mass tends to have more electrons. So London dispersion forces strength will increase as the number of electrons increase. All right, so why is this? As the number of electrons increase, now remember that like charges repel. So the more and more negative charges I get, all right, the more and more potential repulsion I'm going to have. So these electrons are distributed throughout, but they're more easily disturbed. There's a more higher likelihood that two negative electrons will come in contact with each other, or even more electrons will come in contact with each other at any given moment, causing that repulsion. Okay. Electron distribution is more easily disturbed. So if we think about the structure of an atom, those outer electrons, all right, the ones on the outer energy levels are held less tightly to the nucleus because there is an increase in distance, Coulombic attraction, an increase in distance of those electrons from the protons in the nucleus causes a less attraction. They are less tightly held to the nucleus, and we say, therefore, they are more polarizable. Therefore, they are more polarizable. And this is a term that I need to see in explanations, all right? Especially if you get something that goes against the grain. Chances are there's more electrons, it is more polarizable. Those electrons are more easily disturbed. Now, all substances have London dispersion forces to some degree because all substances are made of atoms, and atoms have electrons. So everything to some degree has London dispersion forces. Now the question becomes, which force is the strongest force within that substance? And so let us go back to water once again. All right, water. Here's water. All substances have London dispersion forces to some degree. So water does have London dispersion forces because it has atoms in it which have electrons. It is polar. Yes, it is polar. Therefore, it has a dipole-dipole. It also has the ability to hydrogen bond because we have a hydrogen with an oxygen. Therefore, this has the ability to hydrogen bond with another hydrogen oxygen. Okay, so it also has hydrogen bonds. So if I was to ask you to list all of the intermolecular forces found in water, you would tell me London dispersion, dipole-dipole, and hydrogen bonds. But which one of these is the strongest force? And the strongest of those three is hydrogen bond.